black on, and
but they are already divided, no? They've
already got it, yeah.
So, can I go here?
Just make sure that. Just pop that in there, and just pretend it doesn't.
Okay. Yeah, can I start?
Yep.
Hi everybody. So we will start the workshop. My name is Roberto. I'm a software engineer in the ARM ecosystem. Originally, I'm a nuclear physicist, but I have been working in graphics in 1995 after 10 or 12 years working in nuclear research, where I was doing some nuclear reaction simulations, where you got these nice graphics, where error bars and some graphics, but computer graphics is more funny, because what you code is what you see, and this is why I'm working on graphics. So let's see the plan for the workshop. I know that you got all of you the project loaded already in Unity and so on, but it's important to understand the technique, because otherwise you won't understand what is called there. So we will go through first the concept of cube map, of local cube map. We will see how local cube maps were used from the very beginning to implement reflections, and then we will learn this new shadow rendering technique that we developed in our team to render shadows, which is the main topic of the workshop. We will see the most important benefits of these techniques, also the limitations, and at the end we will go through the project. I will show you the main components of the project. I want you to understand how the shader that implement the shadows are written, or the most important lines of the shaders, and then we will build the project, and we will install the project on the tablets. Do you have the tablets? Okay, so I want you to go through the whole cycle, and then if we got some time, you can play some with the shaders and with the parameters we have exposed, to play with some parameters of the shader and get different lighting effects. So let's start with how we use, or how the cube map were used initially to implement reflections. Cube maps. So raise the hand who knows what the cube maps are. Some of you don't know how what the cube map is. It's just 6 textures, okay? And how we render a cube map. So we put somewhere in the room a camera and take 6 shots in the 6 main orientation: up, down, left, right, top, front, and we build a cube map with that. There are some tools that we provide those pictures and build a cube map for us. And how you retrieve a cube map, how you retrieve a texture from the cube map. So providing a vector, just providing a vector, and internally the cube map will know which texture from which side of the cube is taking your texture. Okay. So when one of the first use of the cube map was for reflections, because it is straightforward. You got your the normal of the reflected surface. You got your view direction, and then there is a built-in already function in CG or in every shaded language to find the reflection vector, and then you use this function here shaded to fetch the texture. This is the cube map, the texture, and you provide the vector. So it was straightforward, very simple, and it was a very easy way to implement reflections. So you bake your cube map once, and then you use the cube map many times. But the problem is that was the cube map works fine when you are dealing with reflections from a distant environment. for example, from the skybox. So, but when you are dealing with reflections in a local environment, for example, in this room, and we bake a cube map, we render a cube map from some point in the room, and we try to implement reflections in a local environment, this is what we get. And those reflections are raw, you see. So the camera is moving along the reflected surface, keeping constant the view vector, moving the camera, and the reflection we get is always the same. If we think a little, if we get back and we check this expression, so if we are moving the camera along the reflected surface with a constant angle, so this vector is constant. So as we are dealing with reflections in a planar surface, the normal is also the same. So the reflections are always the same, no matter where you are. So something is wrong there. What we are missing there is the binding with the local environment, because the reflections not only depend upon the angle and the normal to the reflected surface, I mean the view vector and the normal to the reflected surface, it depends also on the position where the viewer is, okay? And this problem was solved already in 2004 and was improved later in the following way. So instead of using the reflection vector to fetch the texture from the cube map, we will apply the so-called local correction to the reflection vector. So we use a proxy geometry that will simplify our scene. And the simplest proxy geometry is a bounded box, and we will find the intersection of the reflection vector with the bounded box, and then we will build a new vector from the position where the cube map was rendered to the intersection point. We find this R prime vector, and that is the vector we use to fetch the texture from the cube map, and this is the vector we use to build our reflections. So we call that process the local correction to the reflection vector, and in this way we are binding our reflection with the environment, with our local environment. Let's see. What we get here is a comparison of reflections, so when using the local correction and when not using the local correction. So here you can see the reflection is constant, and this is the right reflection. Okay, this is why it is so important when using the cube maps in some local environment to apply the local correction, not only to reflection vector, to any vector we use to retrieve any information we store in our cube map. Because we can use our cube map for many things. We can store there not only in the RGB channel what we got in our local environment. We will see now what we need to store there to implement the shadows based on local cube maps. But before showing that, I would like to just highlight the main difference between the infinite or standard cube maps and local cube maps. Infinite cube maps, they are good to represent the lighting from a distant environment, for example, from the sky, from the sky, in this case, the sky boxes, and they are not. In this case, for the infinite cube map, the position is not relevant. So it's the environment we are trying to emulate with the cube map is so far from us, then it is not relevant where we are. But in the case of a local environment, it is relevant where the viewer is. It is relevant. You need to take into account where the cube map was rendered, and you need to apply the local correction. So in this case, for the reflections will be correct if the objects are near to the boundaries of our environment. So this is why, for example, we will see that in our project for the shadows, I will explain that a little more. But local cube maps, in the case of reflections, are good to implement reflections of objects that are near to the boundaries of the local environment. So let's see now how we use local cube maps to implement this new shadow rendering technique. This technique is based in 2 stages. During the first stage, we will render offline in the alpha channel of the cube map the transparency of the boundaries of our scene. For example, if in this room we will place the camera in the middle and we will render in the alpha channel the transparency of the wall, of all the roof and the floor, and all the geometry. In that case, where we got the windows, we will be completely transparent. In those cases, when we got a completely transparent geometry, we will write in the alpha channel 0, and where the geometry is completely opaque, we will write in the alpha channel 1. For other semi-transparent geometry, we will write some value between 0 and 1. But the most important is that what we will get in our cube map is like a map where the light can come through and reach the inside of our scene. So here we are rendering we are rendering this completely transparent windows, or maybe there is no geometry. Where there is no geometry or the geometry is completely transparent, we will render 0. For the rest of the page geometry, we will render 1. And this is what we do in our cube. So at this point, we haven't considered yet the position of the light or the number of light. So this method will be independent of the position of the light. The only restriction is that the light should be out of the bounding box that delimits our local scene, and it's independent of the number of light. The procedure we will see, you just apply to every light. So that was offline when we are rendering our cube map. So at runtime, what we do is first in the vertex shader, we build a vector from the vertex to the light. We build a vector to light vector, and we pass that vector to the fragment shader as a variable in such a way that vector will be interpolated by our hover. In the fragment shader, we will get the fragment to light vector, and then in the fragment shader, we just find the intersection point of the fragment to light vector with our proxy geometry, which is the bounding box of the scene. We find that intersection point, and we build a new vector from the position where the cube map was rendered to that intersection point, and that is the vector we use to retrieve from the cube map the information we previously stored. We are interested, when fetching the texture from the cube map, we are interested only in the alpha channel value. If there is 1, it means that in the direction from the fragment to light vector, there is an opaque geometry. So the light can't reach that fragment, and that fragment will be in shadows. If when fetching the texture from the cube map and we read the alpha value, and we read there 0, it means that in the direction of the fragment to light vector, there is no geometry, or the geometry is totally transparent. So the light can reach that fragment, and that fragment will be lit. As simple as that. So this is what we implement in our shader, and we will see that. So this is the shader implementation. In the project, it's a little more complicated because we are adding some other stuff there, but basically it's that. In the fragment shader, we build we need to calculate the coordinate of the vertex in wall coordinates, and we build the vertex to light vector, and we pass those as a variable to the fragment shader. Okay? magnitudes we pass as a value into the fragment shader, and this is a fragment shader. So in the fragment shader, we received already interpolated the position of the vertex in world coordinates, and we got already the fragment to light vector. We first normalize that vector, and all the lines which are here is just to find the intersection of the fragment to light vector with the bounding box. You can Google. It is very simple algorithm. In the Wikipedia, you will find, if you Google for vector to box intersection, it is explained in all details. But anywhere, I got a couple of bonus slides at the end of the presentation. We will upload it, and that is explained. For those who like the math, I got explained there every step of how the math behind this. So we find the intersection point here, and then we build the new vector from the intersection point to the position where the cube was generated. We pass as a uniform to the shader the position where the cube was generated, and what else we pass there? The position of the cube map, and we pass also the cube map itself, the texture. So we build that new vector, and then we use that vector to fetch the texture from the cube map, and then we invert that to get the color of the shadows, and then we combine that with the texture, with our texture, or just whatever we put there. It's very simple. We will see in the project, but this is the basis. So why we say that this method, this new technique, provides dynamic shadows? Because when the light position changes automatically in the vertex shader, in the vertex shader, this vector will be updated automatically, and everything will be calculated. So if the light changes the position, the shadows will be updated automatically. And I'm showing here this. So the light is changing the position with this slide. You will have that slide also in the project, and the shadows are updated automatically. Another important feature of this technique is that this technique can reproduce the softness of the shadows. We can render soft shadow with this technique. So it is important, otherwise the shadow won't be realistic. And we can see that this technique, we can get the farther from the object, the softer the shadows. So we can reproduce the softness of the shadows. How we do that? So instead of fetching the texture from the cube map, from the 011 min map, when we bake the cube map, when we render the cube map, we also will build all the min maps of the cube map. And at runtime, we will interpolate between two min map levels. How we do that? So we use this function instead of this function, TextCubeLOD, that will interpolate between two levels of the cube maps. And what we need to provide is some parameter for that. The way we do that is this function expects here a 4-component vector, and the last component, the first 3 components, will indicate the direction, the standard vector you use to fetch the texture from the cube map. And the 4th component will be that parameter that will indicate to the cube map between how to interpolate between two min maps. And what you get when you interpolate between two min maps, we are changing now that parameter now. You see, the shadows are from hard shadows to very soft shadows. Okay? So in practice, we blur the shadows. Okay? So summarizing, what are the benefits of these techniques? It's very simple to implement because the shaders, as you've seen, are very simple. With this technique, we can get this technique is render the shadow faster than other, for example, shadow mapping techniques, 1.3, 1.4 times faster. The quality is very high. Why? Because we are fetching every frame the texture from the same cube map, so we will not see there any flickering or pixel instability in the shadows that we will see in other techniques, and we will see that in the project. Of course, we can compress the cube map. As Sylvester said, we always need to use texture compression. We also, as we render our cube map offline, we can apply any kind of filtering there to get some effect, no matter how complex it is, because we do that offline. It is a resource saving technique compared with other techniques, shadow rendering techniques. Why? Because we render once the cube map offline, and at runtime we are just reading. All the rendering techniques that render to texture at runtime every frame are writing and reading. So this technique halved the bandwidth needed to render the shadows, and it is very important for mobile phones where bandwidth is a really limited resources, and we need to carefully balance very well the use of the bandwidth at runtime. And these techniques, shadow based on local cube map, is very tolerant to the shape of the local environment. Why? Because we are approximating the geometry of the local environment with a cube, with a box. Okay, and in the case of reflections, if your environment is far from the shape of the cube, you will see that your reflections are not too good. In our case, in the project, we have chosen the perfect environment, which is a box environment. But it worked fine because most of our rooms are just boxes. But in the case, but for reflections, when your environment is a little already far from that shape, the reflection won't be correct. But in the case of shadows, it is very tolerant to that change, to that difference in shape. And we showed that in the iScape demo, where the escape was really really different, the geometry of the escape from a box. But this method is really good for mobile, but it has some limitation, and the main limitation is we are building our shadows with a static cube map that is rendered beforehand. If at runtime something changes in your scene, if there are some dynamic objects, we won't get correct shadows unless we update that cube map every frame, which is expensive. In that case, we got a solution for that. And what you do is you use this technique to render the shadow from static geometry, and you use other more common shadow rendering technique like shadow mapping to render shadow from dynamic geometry, and you combine both type of shadows in your shader. This is what we do in our project. So here, the project, you got only one chess piece, but originally I got many. This chess piece is changing the position, so the shadows are rendered using shadow mapping technique, which is rendering to texture from a camera which is located where in the position of the light, and it's rendered to texture every frame. And the shadow coming from the windows, which are static geometry, are rendered using this shadow rendering technique based on local cube maps. This is what we got in our project. So we combine both type of shadow rendering technique. So once you build your project and you install the project in your tablet, you will have the tablet. So in this third, we got 1/3, second third, third third. It's divided also in 3 parts. So here, if you touch there, you will get some virtual joystick, and with one joystick, you can pan the camera. With the other joystick, you can orient your camera, so you will see it's very easy to navigate inside of the room. And then you got two slides to this changes the position of the light, and this changes the parameter that controls the softness of the shadows. And when you've got an object in the central third of the screen, only when the object is there, then you can touch it and move it. Okay? Once you touch it and fetch the object, you can move everywhere. But to start touching it, should be in this third. Otherwise, you can. If the object is somewhere there, what you need to do if you want to move some object is just to pan the camera and see the object in the central third, and then you will be able to touch it and move the object. So let's wrap up and let's go to the project. This new technique based on local QMAP is relevant for mobile. Why? Because it is faster than shadow mapping technique, and it helps the use of the bandwidth. So go for it if you are rendering static geometry only. If you are rendering static and dynamic geometry, combine this technique with the shadow mapping technique, for example. As I said, the quality you get here is perfect because you are fetching every frame the texture from the same QMAP. When you are rendering shadows using the shadow mapping technique, every frame you are rendering to a different texture. And when you will see there in the project that the shadow from the chess pieces has shimmers and has some flickering in the border of the shadow and the light. And we can combine this technique with other standard shadow mapping technique. And the implementation in Unity, as you will see, is very simple. The project, let's see now, you can find more info about the use of local QMAP for reflection, refraction, shadows in those links, which are some blogs that we have written in our team. Those are a couple of bonus slides where you have the implementation of this of the solution of the vector to box intersection. Okay, so let's see now. Let's start our project. So, who is not familiar with Unity here? Who is not familiar with Unity? So most of you have used Unity. Okay, you are familiar with the environment. So there you got already Unity loaded, with the project loaded. You should be able to see the scene. And I will also open my project here. I just want to go very fast through some main components of the project, just to show you where. Okay. So at the left we got the hierarchy of our scene. So in the scene mode, we can click on the reflective surface. If you click there, you will see on the right, which is the material applied there, and you can edit the shader. So this is the shader that implements the shadows on the room, on the walls, on the floor, on the so everywhere in the static geometry. And I want to go a little through the shader to help you understand a little the shader, and then you can play with it. So here in this block, we are listing all the magnitudes which are visible, which are accessible in the shader here. You see, we got the main texture. There is also the texture that we are rendering. We are rendering at runtime. If we play our scene, if we play now, we will see how this texture is populated. You see, because this is the texture from the chess pieces which are rendered every frame to use the shadow mapping technique. So if we open, you see. So this is what we are rendering for the shadow mapping technique from the position of the light. Only we are rendering the shadows only from the dynamic objects in this case. So we'll go back, select this, and we got also the cube map, and we got a couple of other factors that we use in our shader. So those magnitudes are there in the property block, this block. And then it goes our shader. Here we are declaring all our uniforms. The uniforms that you know as they are like a global variable that are that you can access in your fragment, in your vertex and fragment shader. Okay. The uniforms, which are for the shadows, we use the position of the bounding box. You see the bounding box, min and max position, minimum and maximum position, minimum and maximum vertex of the bounding box, the position of the bounding box, then the cube map itself, the position of the light. We need to pass to the shader the position of the light every frame, because we can change at runtime the position of the light, and some other parameters we use to control our shadows, but they are not so relevant, just to implement the technique. And for the dynamic shadows, we pass, of course, the texture, the shadow texture we render to, and then some view projection matrix we need to have in our shader to project, because we render the shadows from the position of the light using the shadow mapping technique, but we need then to project those shadows onto the chessboard. So, and then we got here some other uniform. This is a light to shadow contrast. Some other stuff we just used to make it more effective, to add some other additional effect to the shadows. So this is the structure. We are using only the vertex, the texture coordinates, and the normals. That's all. That's very simple. And this is the output structure from our vertex shader. And this is what we do in the vertex shader. We calculate here the position of the vertex in wall coordinates is here. The normal in wall coordinates is here. And then okay, this is the final position of the vertex. We need all the way from the vertex shader to output the vertex after applying the model view projection matrix. And yeah, we need that also, the vertex to light vector in wall coordinate, and this is the vertex in screen coordinates. Okay, so we pass all these to the fragment shader. The magnitude we pass as a variant to the fragment shader are interpolated by the Howard, so this is very efficient interpolation. And in the fragment shader, we got already access to those magnitudes already interpolated. So in the fragment shader, we initialize our final color. We get the normal already interpolated. We receive the normal already interpolated. We fetch the texture color, the color just from the texture from the chessboard. We initialize some shadow color. This is not a color, it's just a float. And this is the position. I mean, we initialize position in wall system. So it is the already interpolated vertex position in world coordinate. We normalize the vector, the fragment to light vector, and what we do here is the following. We calculate the dot product between the normal of the normal in the fragment, the normal that has been interpolated. We pass the vertex normal to the fragment shader, and we find the dot product between the normal and the vertex to light vector. Why? Because if we got some, that I will show you in the here. So we don't want the back part of the windows, for example, here, to be lit. There is no point. So we check if the normal of that surface is pointing out from the, in the opposite direction from the fragment to light vector. So that fragment can be lit. So we exclude from the calculation those fragments because it is obvious they can be lit. This is why we add some big if there. So only if the dot product is positive, somehow they are a little aligned or more aligned. But we add some threshold there, and you will. I won't explain everything now, but just tweak that threshold, and you will see in the borders of them. Somehow here, if you go there very close there, we are in the game. So there is a README file with a detailed explanation of everything again. But if you go there and you play with the threshold, you will see why that threshold is important. It's just a matter of detail, no? Okay. What else? What else we got here? So then, if somehow that fragment can potentially be lit, no? Then we check using this technique if this fragment is really lit or in shadows. How? So we use there all the calculation of the local correction are put inside of this function. That function is implemented in include file for this shader. Where it is here. If you go to that, if you open that that file, there is implemented that function. That function just implements intersection point of the fragment to light vector with the bounding box, build a new vector from the position of where the QMAP was rendered to that point, and that function returns the already local corrected vector. So that function already returns that local corrected vector, and in the fourth component return a parameter that we will use to control our the softness of the shadows. Just have a look later to the implementation of the function, but it implements what I have explained before. So once we got already our vector, we get the the x, y, and z coordinates to corrected vector to light. And we use that vector to fetch the texture from the QMAP. We use that. Okay, let me check. We separate the XY component Z and Z that we will use to fetch the texture from the QMAP, and the fourth component we multiply by the parameter we exposed in the shader, just to play with it. No, we add that there, and at the end we build the fourth component vector, and we fetch the texture from the QMAP using this text LOD function that will interpolate between QMAP between two consecutive minimal level of the QMAPs, and give us the texture. So this is the shadow color this is a temp color. We subtract. We are only interested in the alpha channel, and then we multiply again that shadow for some shadow factor that we can tweak, and we get the shadow color here, and we combine the shadow color. We interpolate a little. We interpolate that to make it a little smooth, to smooth the especially when in the region where you got the normal of the surface close to the threshold. We use that to interpolate and make it a soft transition of the shadows. But this is just a tweak on top of the basic of the technique. In principle, you don't have to do that. And then we use the shadow color. We combine the shadow color with some tint. Again, this is something we do on top of the basic of the technique to make it more dramatic, the color of the shadows and so on. And finally, we combine here the color of the shadows with the texture color. That's all. We add there the ambient color and some also some other parameter, the contrast, some contrast color. But all this is just to make more dramatic the shadows. But the basic is what is the code that I show in the script, in the slide. Can be okay. So this is the okay. Let me see. This is the shadows that. Let me show again something here. So in this shader also get the texture rendered by the shadow mapping technique and project using that function. Project that texture on the on our chessboard, and then we get that dynamic shadow color. So that the dynamic shadow color, which is coming from it is a shadow from the chess piece, is combined with the shadows from the static geometry. So you can play later with this shader, and for example, you can eliminate the shadow from the chess piece, or only render the shadow from the static geometry or the dynamic geometry to see how it works. Okay, and this is the shader for the walls and the room, and the shader for the chess piece, which is this one. You can get that shader by clicking. I will stop here. The scene. You click on some chess piece, and then you get here the material, and you can edit the shader. It's simpler because the chess pieces will only receive shadow from the static geometry. So we are not calculating here the shadow from one chess piece to another on top of the other chess piece. We are simplifying this. No? So the chess room can receive shadow from the static geometry and can receive shadow from the chess piece. The chess piece itself can receive shadows only from the static geometry, from the windows. No? And so that is the basic of the implementation of the shaders. And here, let me just show you. So we got the geometry here, all the castles. So this is the geometry from the chess room, which is the static geometry. This is geometry from the chessboard, and we got here the point light. So if we run here, we can change the light position with the point light selected. We can change the light position here, for example, you see, and everything is running. We can change that also. So I got there some sphere, which is right now is disabled, but you can enable, and you can see, you will be able to see. It's like yeah, just to visualize where the light is. Let me see. Oh, it's there. You see, it's there. So you can now, if you select the light, you can now change the light position a little. You see. For example, you can go back and see how the shadows changes. You see. You can see now. Okay, but by default it is this sphere is disabled. We got this unified shaded control where we can control some magnitude that affect all the shaders. But I want to show you something now. Here in the point light object, in this point light, we have attached this script, which is the dynamic shader creator. So this dynamic shader creator will create on demand the shadow mapping camera and the shadow mapping texture. So this is the reason you won't see here the shadow mapping camera. But if you run, if we run here, let me check. You see now, this is the shadow mapping camera, which is built at runtime by this script, which is attached to the point light. This script, dynamic shadow creator, is responsible for creating the shadow camera and the shadow texture, and it just update the position of the shadow camera every frame, because the shadow camera should be located, positioned in the position of the light, as you know. This is a room, the bounding box of the room. It is not rendered, of course, but there is, and this, we render the cube map from the center of the room bounding box. There are some GUI elements, which is the screen resolution. You can change the screen resolution, but it's better to left joystick, right joystick, some Mali logo that is displayed at runtime on the device. This is the script that change the position of the control the touch on the screen to change the position of the chess pieces, and this script send to the shader some information, and that's all. That's all. So what we will do now is, okay, let's build our. Just follow my. I will do the same here. So we will go to File, Build Settings. We need to select Android as the target platform. So we don't overwrite any texture. All the texture are compressed using ASTC texture compression. And we select. Do you have your tablets there? Huh? Where are the tablets? Gemma, where are the tablets?
Everybody should have tablets that you received at registration.
Huh?
What is the IP manager? And in here, apparently, all of you have been given a tablet once you sign up.
Huh?
But the whole point was to bring them for the workshop.
They just always give it stuff like that to throw it around.
Okay, so in here then. Josh.
Okay. So there is no way we can do that, or we can bring the tab. So.
Yes, they all have the tablets. Like, they all have the tablets, but they left it at their own place. They didn't bring them here. It's crazy.
So you will do that at home, probably. You can download the project as it is from the Unity Asset Store. You just Google for shadows, dynamic shadows based on local cube maps. You download the project, you import the package, the Unity package, and this is what you will get. Exactly, you will get this project. So once you are ready, you connect your tablet with your laptop or your computer, and you just press build and run. Before you build and install your APK on the device, you need to check that the device has been recognized by your that the tablet has been recognized by your computer. Do you know how to do that? Using the ADB command, ADB. You should have the ADB located in the Android SDK, in the tools. Have written somewhere there. Tools. Do you know where do you have the? Let me check just to point you to exactly the. So platform tools. So in platform tools of your Android SDK, there is the ADB, adb.exe. So you use ADB devices. Once you connect to your USB port, and it should detect the tablet. If you got problem for that, sometimes you can get some problem for that. In the instructions, we deliver some instruction file and pointing to some download page where you can download driver. Driver, and that will fix any problem. Yeah, that's all, and then you will get something like, let me see if I got my tablet here. This is exactly the tablet you have received. I don't have it installed here, but I can install now. Any of you, do you have a USB cable? Do you have it here? No? Okay. No one of you have the tablet here, no? Have you installed already? Oh, you see, no? Okay. Do you have a USB cable? It's working. It's working on your phone. Is it working fine? Okay, that's nice to hear that. So at one time, you will see, you don't see here in the editor mode, you are not seeing here the logo, Mali logo. You won't see here the virtual joysticks, but I'm simulating the joystick with the mouse, and you will see how it is implemented. Because working on the editor, I can pick an object and move it. I'm just simulating in the script. I detect if I'm working on the editor or at runtime of the device. If I'm working on the editor, I just emulate everything with the mouse. So, and also the navigation, you can navigate with the keyboard arrows, but on the device you will need to navigate with the virtual joystick. Okay. So I will do myself here. Okay, I will show you. Do you need to go now? Sorry?
Announce this defeat in a little bit.
Okay. So thank you guys. Thank you very much. Thank you.
as you keep hold of it. It's no fun. With the without I don't know if you explained it. With the scene, yeah, when you run it, how comes the shadows flip?
Sorry. No. We can. How? Sorry.
When you go to the scene view,
Yeah.
the shadows of the rooks are flipped. So the head of the castle is at the back.